Okay, great. So yeah, my name's Liam Connor. I started here at Harvard University as assistant professor about 6 weeks ago. I'm not a CGM person, but I would like to be eventually, if you'll have me. So I'm going to tell you about some recent results on mapping out the universe's cosmic baryons using localized fast radio bursts. So just very quickly, by show of hands, who is familiar with this concept of using FRBs to go after the IGM and CGM? Okay, this is great. I can go through the introduction fairly quickly. Here's a typical FRB. It's dispersed. Lower frequencies arrive a little bit later than higher frequencies. And that's due to all the ionized plasma through which the burst travels. So the dispersion measure is literally just the line of sight integral of free electrons between us and the source. And this is a collapsed quantity. It includes the Milky Way's ISM, the Milky Way's CGM. The IGM is usually the lion's share for most cosmological FRBs. And then the FRB is going to live in some host galaxy with its own ISM or maybe some circumsource plasma. And along some sight lines, you'll intersect an intervening galaxy's halo, and the CGM is going to contribute some dispersion measure. Of course, the amount of DM that it contributes is unknown, and how that varies with impact parameter is also unknown. Okay, so at the population level, if I go out and I localize a bunch of fast radio bursts, I'm going to have a set of pairs of DM and redshift. And if I have a perfectly smooth universe with no large-scale structure and no halos, there's going to be a one-to-one mapping between redshift and extragalactic DM. If I add in halos, then now I'm going to intersect intervening galaxy CGM, or maybe not, or maybe a few. And so I add scatter to the line of sight DM. So for a fixed redshift, I can get different DM values. And this is a very noisy thing. You know, it's very Poissonian. You can intersect 0 or 1 or 3, and so you end up with a lot of scatter. If I have a more realistic universe, where now I have large-scale structure in the IGM, including filaments, sheets, voids, et cetera, and if I use something like illustrious TNG, then now I have scatter as well, but because the IGM is relatively smooth compared to intersecting halos, there's less scatter. So if I use, say, 100,000 sight lines instead of 50, it'll look something like this. And I just want to highlight this thing that we sometimes call the DM cliff, which basically just says for a given redshift, there's a minimum DM that you're going to see due to the IGM. And that's because if you're sufficiently far away, you're going to intersect many filaments, and even the voids are full of gas. So you'll get some DM contribution from them as well. If I change the gas parameters, if I go from 80% of the universe's baryons in the IGM to, say, 60, something that resembles the sort of dark matter distribution, where roughly half of the dark matter resides in virialized halos, then I'm going to have a much puffier distribution. I still have a DM cliff, but it's lower. And so the claim is that with a population of localized FRBs, where you have these DM redshift measurements, you can actually distinguish between these scenarios fairly easily. Okay, so with the Deep Synoptic Array, or the DSA 110, we now have the largest sample of localized FRBs. And again, localized kind of means arc-second precision. You follow it up, find a host galaxy, get its redshift. Some are quite nearby, some are farther away. Some are hostless until we observe them for like 5 hours with Mossfire. Some are right next door. This one we call Mark. It's only 50 megaparsecs away. Right, so the IGM is doing basically nothing. It's mostly being dispersed by the Milky Way's ISM and halo. And a number of them clearly intersect the CGM of foreground galaxies. Okay, so if we go back to the sort of population analysis, this was roughly the state of affairs 4 years ago. This is the McCart relation, which used just these 5 localized FRBs to show that the DM really did seem to be coming from the large-scale structure, halos and the IGM. It wasn't that FRBs were being dispersed by host galaxies, because there's this clear trend for more distant sources to have more DM. Now, you can't really do a partition. You can't say this fraction is coming from the halos, this fraction is the IGM, but it's at least trending in the right direction. If I expand the axes in both directions and replot it, it looks like this. And then if I plot our sample, it looks like this. So we have an order of magnitude more, but we also have sources that go to and actually extend past redshift 1. So we have a much longer baseline. The background is just going to be a 2D likelihood function, which basically tells you what's the distribution of DMs I can expect at a given redshift for fixed cosmic gas parameters. So if I vary those gas parameters, and again, put more gas into the halos, I end up with this puffy thing that we saw before, and this is clearly not really well fit to our data. Conversely, if I put way too much gas in the IGM, or maybe I get omega B wrong, then again, this does not fit our data very well. If I run the actual MCMC fit, I find that FIGM is maybe 80%. You also note that this sort of nuisance parameter of the host galaxy DM contribution is pretty modest. The median host DM is going to be of order 100 units, not several hundred units, which would add a lot of noise and actually hurt us doing this in the future. So I have the 80% number from the FIGM from FRBs. If I import other precise measurements of the hot gas in the universe, say with massive group and galaxy cluster catalogs, I find that maybe 9% of the universe's baryons are in massive groups and halos in the hot phase, or in clusters, excuse me. We can also incorporate what we know about cold gas, most of which is H1. It's about 1 or 1.5% of the universe's baryons. So the kind of striking thing is that just with the IGM, massive halos plus cold gas, we've already accounted for 90% of the universe's baryons. So there's only 10% left for all stars and the CGM. Okay, so here's the kind of full partition as a baryon pie chart. Most of it's the IGM, maybe 10, 15 odd percent are in the halos. And as of 10 years ago, that pie chart would have looked something more like this, at least in terms of the media that we could directly measure. These are the numbers from Mike Shull's 2012 paper. So we've not only kind of accounted for the so-called missing baryons, but we've actually partitioned them for the first time. If you ignore the partition and you don't try to break them up between the IGM and the halos, you can also just measure the total fraction of the universe's baryons that are diffuse and ionized. So count up electrons that actually contribute to DM. So this does not include stars, for example. And you can do this cute little thing, which is you can place an upper limit on the total stellar mass of the universe without having measured a single stellar photon. And therefore, you can rule out certain IMFs. And so because we're seeing so much dispersion measure effectively for this cosmic sample, you can rule out bottom-heavy stellar initial mass functions, for example, saltpeter with a minimum mass cutoff of 0.1 solar masses. We get a sub 10% measurement on omega B. Thanks. But to draw this back to the sort of purpose of the workshop, if I compare these results with simulations, you'll see that in Simba, for example, if you turn off all feedback, FIGM gets as low as 60%. In the sort of standard suite with strong feedback, this is more like 85%. And so clearly, the fact that we're seeing a large fraction of the cosmic gas in the IGM indicates at least some efficient feedback processes that can expel or prevent gas from falling into halos. And this seems to be in line with other statistical measurements of similar things. So on the left is a very recent KSC galaxy cross-correlation, where they find strong evidence against gas tracing the dark matter distribution. On the right, this has been mentioned a few times already, but an X-ray stack of something like 100,000 Milky Way-like galaxies finds that the hot gas fraction of these halos is well below the cosmological average. So just to summarize these findings from a sample of 50 localized FRBs, we have this partition of the universe's baryons, fully accounting for omega B in total. We get this fun little constraint on the initial mass function, ruling out very steep bottom-heavy IMFs. We get omega B to 10% in agreement with early universe constraints like Big Bang nucleosynthesis and the CMB. And then finally, kind of by process of elimination, we can put constraints with very wide error bars on the total gas content of the CGM, at least the portion of the CGM that can contribute to the dispersion measure of FRBs. Okay, so this was done with of order 50 localized fast radio bursts. In the next few years, we should expect this number to increase to many thousands. And by the end of this decade or the beginning of the 2030s, that number could be 100,000. And you'll note that in this analysis, I've really kind of focused on the IGM. I haven't included any information about galaxy catalogs, at least for those sightlines. And so in the future, what you would do with these upcoming surveys like CHIME VLBI, CHORD, and the DSA 2000, which I work on, is you would actually do some sort of stack or a massive cross-correlation against, say, DESI, and you could start to say something about the distribution of baryons around these halos, not just this very low-resolution claim that I've made, which is that 80% of the gas is outside of halos. So with that, thanks a lot. Happy to take questions.
Very interesting talk. Can you give us any constraints on the temperature of the CGM gas ingredients might be tracing?
Unfortunately not with FRBs alone. We did this thing last year, which is we found the first FRB that resided in a galaxy cluster. And it was significantly overdispersed, presumably by the ICM. And so by combining that with an SE detection of the same galaxy cluster, you can kind of divide the two and get an estimate for line of sight temperature. But yeah, the FRBs are going to be sensitive to anything that's ionized, basically, and non-relativistic.
How many FRBs would you need to study the time evolution of your pie chart?
Oh, that's a really good question. Yeah, I mean, the size of the sample matters, but then also the redshift distribution will matter. And there's pretty good evidence that the deeper you go in a radio survey, the farther away the mean FRB will be. Mm-hmm. So it seems pretty likely that the next batch, once we're at 500 or something with more sensitive telescopes, they'll go well beyond redshift 2. Presumably FRB emitting sources exist back then. Mm-hmm. In which case you can start to look for changes in FID and everything. So.
Does Daniel want to come up next? Any more questions?
Presumably, this will come with the samples that you are going to have. What are the close by FRBs, kind of analogous to the different absorption that we were talking about earlier today? That you'd be able to look at along similar lines of sight.
Yeah, that's a neat idea. I mean, so the DSA 2000 will have deep drilling fields where it'll find very high aerial density of FRBs. So it'll be fun to do similar things. I mean, the best would be to have a strongly lensed fast radio burst, which only has different dispersion measure from the CGM of the lens galaxy, in which case you can do some really interesting models or modeling.
Do you have any more questions? So, how long do we have to wait till we get all this new data?
So I think it depends.
No pressure. But.
Yeah. The fastest turnaround, I think, will be CHIME VLBI. So CHIME is a single interferometer, very compact, it's got poor localization. They've expanded and now have VLBI outriggers, and as soon as that turns on, it'll be 1 a day or something like that.